Memory today is cheaply available and is getting cheaper and cheaper. But applications are demanding more and more memory. Therefore, there is never enough memory. Memory management involves here swapping blocks of data from secondary storage. So here we are swapping the data blocks from the secondary storage to the main memory, and to and fro occurs frequently. Memory management includes here IO devices. Here memory IO is slow compared to CPU. The operating system must cleverly time the swapping to maximize the CPU's efficiency. Memory needs to be allocated to ensure reasonable supply of ready processors to consume available processor time. Now we'll look at the memory management requirements. The points that will be discussed here is relocation, protection, sharing, logical organization, physical organization. First we will look at the first requirement, that is relocation. Now here the programmer does not know where the program will be placed in memory and when it is executed. As being a programmer, we don't know where actually the program will be placed into the memory and when it will be brought into execution. It may be swapped to disk and returned to main memory at different locations. When we when we do not need that program to be in the memory, it is swapped back to the disk, and it is not necessary that it will occupy the same memory location from where it has been brought into. Memory references must be translated to actual physical memory address. Now here is the table showing memory management terms. We will be using these terms. We'll be using the term frame to describe a fixed length of block of memory. Page is used to describe fixed length block of data in secondary memory, that is on hard disk or magnetic tapes. Segment is used to describe variable length block of data that resides in secondary memory. Now this figure shows you addressing, how we can map here the physical address or the logical address of the process into physical addresses. So just have a look at this figure. Here we have a section of memory which is called as program control block. So there, PCB, it has got some sort of information about the processes that have been stored or loaded into the memory. Then there comes the next section, that is program section. So all of the code in the process that is executable is written over this, is saved here. Then you have data section, which while execution data is required, so the next section is referenced here to acquire the data from you. And this addressing values increases from top to down. Then again we have a section called as stack for temporary holding the values. The next point in requirements is protection. Processes should be able to reference memory location in another process without permission. If those processes are able to reference memory locations in some other processes without permission, how about protection? So it is impossible to check absolute addresses at compile time. So these can be checked at runtime. Then sharing allows several processes to access the same portion of memory. By sharing, we are allowing several processes to access the same part of memory. Now, better to allow each process access the same copy of the program rather than having their own separate copy. This will save the memory here. Looking into logical organization, memory is organized linearly. Usually memory is organized in a linear fashion. Programs are written in modules. Now modules can be written and compiled independently. There are different degrees of protection given to modules, as can be read-only, executable, write-only. These are the degrees of protection that we apply over the modules. Now these modules can be shared among processes, and this helps in segmentation. Looking towards the physical organization, we cannot leave the programmer with the responsibility to manage memory, as it is not the job of programmer to always keep in mind whether the program it is writing will take lots of memory or not. And always is go for program optimization. Memory available for a program plus its data must be insufficient. Whatever the memory space is available for the program and its data, it may happen that it is not sufficient. There can be overlays that allows various modules to be assigned the same region of memory, but is time consuming to program. So programmer does not know how much space will be available for the program. Knowing all these problems, we can go for partitioning. An earlier method of managing memory was pre-virtual memory, and it is not much used now, but it will clearly clarify the later discussion of virtual memory if we look at first partitioning. So here by partitioning we mean that we will be dividing the memory available with us into various sections. Virtual memory has evolved from partitioning methods only. Now there are types of partitioning. We have fixed partitioning, dynamic partitioning, simple paging, simple segmentation, simple virtual memory paging, and virtual memory segmentation. We'll look at all of these one by one. Now, see here a figure has been shown to the right hand side. This demonstrates fixed partitioning method. We have equal size partitions. We have divided the memory into equal size blocks. Any process whose size is less than or equal to the size of the given partition can be loaded into an available partition. Now look at this. Each block is of 8M. So any of the process which is having size less than or equal to 8M can be loaded in any of the free partitions. The operating system can swap a process out of a partition if none are in ready or running state. So it depends on operating system can take this decision that which of the process can be swapped out and which of the processes can be swapped in based on their status, whether they are in ready state or in running state. But there are problems with fixed partitions. A program may not fit in a partition. If there arises a situation where we have processes whose size is quite greater than the available partition, then in that case that particular process or program may not fit in a partition. The programmer must design the program with overlays here. The situation has to be overcome by introduction of overlays. Main memory use is inefficient. The second problem associated with partitioning is the main memory use is inefficient. We are unable to use the main memory efficiently. So any program, no matter how small, occupies an entire partition. In this case, this will result in internal fragmentation. No matter how small the size of program is, it will occupy one of the block of the given size, that is of fixed size. And once it is allocated to that program, if the size is too small, still it is allocated to that particular block of memory, then it will ultimately result into internal fragmentation. The solution can be thought of as unequal size partition. Rather than going for equal size partition, we can adopt unequal size partition. This will somehow lessen the problem of internal fragmentation. See here we have variable size partition 2M, 4M, 6M, 8M, 12M and 16M. So whichever size of partition is nearly equal to the size of the incoming process, that partition will be allocated. So it will somehow minimize the problem of internal fragmentation. Now here we have placement algorithms. In case you are using equal size partition, the placement is trivial. That means you do not have any other option. And when we are using unequal size partition, the process can we can assign each process to the smallest partition within which it will fit. And we can also have a queue for each partition. The processes are assigned in such a way as to minimize wasted memory within a partition. Now this figure demonstrates fixed size partitioning and having a queue. Now for each of these partitions we can maintain a separate queue, but then it will require some additional memory here. So one process queue per partition, this is an arrangement, but then as I said, it will require additional computation as well as memory spaces. Here we have a single queue in which the jobs will be placed and a suitable partition will be allocated to it. Still, there are remaining problems with fixed size partitioning. The number of active processes is limited by the system.